Okay, so it's great that so many people could actually stay for the final session. And I'd like to start, of course, by thanking the organizers for not only inviting me, but for setting up all this great program here. So I learned quite a lot last week during the school, this week during the conference talks, and now it seems that it is my time to share something with the others. And I'm going to talk about the research that I'm involved in together with my supervisor Nicholas Barzot at ETH and with Matteo Rosso, who is now a postdoc here at Humboldt. And the project itself started already more than a year ago. So those of you who went to London last year might remember Nicholas's talk that showed some preliminary results. The good news, however, is that I'm not going to assume that you remember anything from this particular talk. And so for the couple of next slides, I would like to give some motivation and recap, well, the knowledge of Yangian algebras, and also finally show you the results that Nicholas presented in London. Good. All right. So as we know from the research that originated in the, well, roughly 2000s, many observables in n equal 4 super Young mills exhibit Yangian symmetry in the planar limit. So perhaps the best known example would be the scattering amplitude, when a dual superconformal symmetry was shown by Drummond, Hand, and Plefka to actually indeed be a Yangian symmetry. And so the question that we wanted to ask and well, answer before anyone else is, could we in some sense say that this symmetry originates from the action? In other words, can I make sense of this equality here, and is it true? And for those of you unfamiliar with Yangian algebras, here is the super short introduction. So we already encountered Yangian algebras this week on Tuesday in a beautiful talk by Aleksander, but he relied on the second realization. I need the first one realization by Drinfeld. So what do? Well, we start with our usual symmetry algebra or superalgebra. In the case of n equal 4, this is PSU 224. And then we introduce another set of generators. So we indicate them by putting a hat on top of them, and they basically satisfy a similar commutation relations to the original levels, well, generators of the Lie algebra. So J with J hat gives me a combination of J hat. And the hatted generators are called level 1, and therefore the unhatted ones are level 0. And then if I commute to level 1s, I get level 2, etc. So this is rather simple. There are of course some Jacobi-like identities that the level 1 generators satisfy, but I'm not really gonna concentrate on them. What I need, however, for the rest of the talk is the co-product of level 1 generators, or to say in a more physical terms, the action on the multiparticle state. So what happens if I have two sides sitting next to each other? And here it is. So in addition to the trivial part that you would have even for the level 0 generators, you also have a bilocal part where you can see two level 0 generators acting simultaneously. And as we will see later on, this is a source of all the problems that we encounter. All right, so now we know how to act. So, well, we boldly take our action and immediately run into trouble. Why? Well, first, because the action is cyclic. So we have seen the n equal 4 action already a couple of times this week. So I refrained from putting it here again, but the important part is here, and is the trace. And trace imposes cyclicity, and it is kind of well known that Yangian generators are incompatible with this property. So depending what I pick as my first side, I'll get different results, and that doesn't make sense. So this is our first problem. And the second problem is that, as I mentioned already before, Yangian symmetry appears only in a strict planar limit of n equal 4. However, well, the action generates for us both planar and non-planar contributions. So the question is, how do I actually pick out only the planar part? And so last year, we managed to circumvent already the first problem. So, well, you can't act on the action, so what is the closest thing that you can think of to the action that is no longer cyclic? And those were the equations of motion. So by varying the action with respect to a field, you, well, break open the trace, and the resulting object is of course no longer cyclic. And what we showed is that the action of p hat, so a level 1 momentum generator, whose bilocal part of a coproduct I gave you there, annihilates on shell all the equations of motion of n equal 4. So this wiggly equality here means that, well, in the computation of the left-hand side, I liberally used all the other equations of motion of a theory. And that was the status 1 year ago. So let me now tell you where we are 1 year later. So I already told you how we could circumvent the issue of cyclicity of the action, and in order to address planarity and also to develop the program further, well, we need to better understand, well, how we actually act with the Yangian generators because of already mentioned non-trivial coproduct. So you can see the dots. Well, no, I mean, it's not like I took equation of motion, set it to 0, and then acted with p hat on 0. I was surprised I get 0. Well, what you write down the, well, say, ds over dz, but you don't put that on shell yet. You apply your generators, local part, bilocal part, and then the resulting expression is 0. So if p hat is a symmetry, well, this statement is obviously true, but it need not be. When in principle you can imagine, well, take an equation of motion, applying some weird transformations to it, and you end up with something that is not proportional to any other equation of motion. But, so this condition here that I have, that this is, well, weakly 0 if you wish, is certainly a necessary condition, but by no means a sufficient condition for p hat to be a symmetry of the action. But this is where we were a year ago. Now we're a bit further. Yes, so as I was saying, we have a non-trivial coproduct for our level 1 generators, and as you can see here, if I iterated n minus 1 times here to act on an n-fold tensor product, well, I have this sum here, and it works nicely as long as you have a linear representation of your symmetry algebra, meaning that it always takes one side to one side. However, it's not actually a standard or a best choice for gauge theories. Well, because of their gauge symmetry. So for, well, level 0, the symmetries, the usual Lie algebra symmetries, the most convenient choice is to pick a representation that would preserve for us the gauge invariance or covariance of the objects that we act on. So, for example, for momentum, instead of picking the usual partial derivative as a generator of translations, you would pick a gauge covariant derivative. And then the problem is that the algebra closes only up to gauge transformations, and most of the generators act non-locally. So, for example, this is supersymmetry acting on my field psi. I get F, which is, well, bilocal in field, well, which has two fields, and a piece quadratic in scalars. So this is a nice choice because, well, gauge invariant or gauge covariant things remain such, but we multiply the number of fields by performing the translations, the transformations. And for our level 0 algebra, for the usual, well, PSU 224 in this case, it's not too much of a difficulty because, well, what you can do, you can basically quotient out your gauge transformations without any difficulties. And here I have a picture. So if I have a linear action, start with, well, 5 fields in this case, take them to 5 fields, nothing happens. If I have a 1 to 2 action, well, I take 5 fields to 6 fields, but it's still rather simple to work with. So nothing bad happening here. However, if I go to level 1, then I might run into trouble because if, well, you see that if one of those generators here changes the length of the object we act upon, then the sum here also changes, And if L actually increases the number of sides, then which side actually the kth generator acts on? Do I take the initial ordering, or do I take the updated ordering by the action of the previous one? And it turns out that the answer is actually not that easy. We were lucky in the beginning because it proved, well, while acting on equation of motion, or equations of motion, it turns out that the simplest prescription works. You take your initial ordering and don't worry about what happens afterwards. However, when acting on other objects of the theory of our interest, we will see that the generators start to overlap. And before I explain what it is with pictures, let me just quickly mention what happens here. So you see that I applied my level 1 generator, well, to a commutator of fields, and what I get on the right hand side from the bilocal part is an anti-commutator. And this is basically related to the fact that level 1 generators change parity. So if I had two bosons here, well, then I may end up with two bosons in an anti-commutator. And this will pose some interpretational problems towards the end of the talk. But here are the promised pictures. So there are basically two possibilities. Either I get a bilocal action without overlap, so this is like, well, J1 and J2 in Sweedler's notation, and I took two fields into four fields here, but that's still okay. Or I had an overlap, where I took first one field to two fields here, but then the second generator, J2, acted on one of the resulting fields. And as I already mentioned, that doesn't happen when I act on equations of motion, but it does happen when acting on different, well, on some of the other observables. And furthermore, it's very hard now to say what is a gauge transformation and what is the action of a global symmetry. But already with the knowledge that I gave you, we can address the issue of planarity. So the slide is actually about equation of motion, but maybe it's even easier to think in terms of the action. So the action is a trace of a product of matrix valued fields. Let's take UN or SUN, well, UN in this case maybe, and what you know you have is some trace identities between the powers of your generators. So you can think of like Cayley-Hamilton theorem from the algebra. And those relations could allow you to change the ordering of your fields. But you don't want them, because in this non-trivial part of a coproduct, we had a definite ordering. And if we change the order of fields, then the results will be different. So in order to have a definite ordering, so which field stands next to which one, we basically have to have an algebra that is sufficiently large for us not to run into, well, trouble. So you could think that, well, since in n equal 4 the maximum term has length 4, like 4 scalars, well, that U6 might be enough, for example. But you saw already that my generators increase the length of the objects they act on. And, well, level 1 generator already took 2 fields into 4 fields. But then I want to be able to apply also level 2, level 3, up to infinity, and then they will expand the thing even further. So in order to really have a definite ordering for every possible Yangian generator, we basically have to take the large n limit. So this is the comment I can offer on planarity. And now let's address the question that Nikolai already posed, namely, well, when is a symmetry of the equation of motion a symmetry of the action? So in the other direction, it's rather simple. Whatever is symmetry of the action you have, it will also be a symmetry of the equations of motion. Well, in the other way, however, it's certainly non-trivial. So it's very simple to answer this question when you just consider the algebra generators. So you start with J, well, being the symmetry of the action. So this is the statement here, and you just, well, differentiate it once with respect to an arbitrary field. And you end up with the following formula. J acting on equation of motion is equal to, well, this right-hand side. And this right-hand side, as you can see, is a specific combination of equations of motion well, given by the representation, in this case, of J on the fields of your theory. And then you can, well, take your favorite theory and convince yourself that all the symmetry generators, well, all the symmetries of the action will satisfy this formula, and the remaining symmetries of the equations of motion you could think of will not satisfy it. So basically, well, we call the, well, this formula the strong invariance of the equations of motion. It holds off shell, so I don't use any equations of motion here. If I use them, well, then the right-hand side is again 0, simply because this term drops out, well, becomes 0. And, well, it's pretty much equivalent to J being the symmetry of the action. So now the question was, can we lift it to level 1 generators? So in order to do that, well, we had to restrain ourselves from, well, freely using equations of motion in the initial computation and express the right-hand side here as a combination of, well, equations of motion and something. And indeed it turned out, well, that it's possible. So you have here this anti-commutator appearing that I already discussed a couple of slides ago. And the question was, does the right-hand side actually follow from a formula similar to the one that I just derived for the usual Lie algebra generators? And fortunately the answer was yes. So lo and behold, this is the magic formula. And well, you can immediately see, due to the appearance of equations of motion here and there, that if I set it, well, if I put my fields on shell, I get 0, as we already had a year ago. However, this statement is much more powerful, well, by analogy with what I just derived for you. And well, you can observe that the right-hand side, of course, has two terms. So the first one is a direct counterpart of the one that already appeared at level 0. So it has just a local action of my Yangian generator on one field. And the second part, or the second term, is a result of, well, the bilocal part of a coproduct. And the interesting part of it is that first, it vanishes, it's non-vanishing only if JC here acted non-linearly, so it took my field appearing here into at least two fields, simply because you have two variations here. But what is even more interesting is that this is already an example of overlap of two generators, because you see I had JC acting on fields here, on Z here, producing me at least two fields. But then I only replace, well, I only act with JB on one of them. So this is a rather curious fact, because on left-hand side, we never had overlapping generators, as I already told you. We took the simplest prescription we could think of, and yet the right-hand side produces overlaps. But still, this result correctly reproduced all the right-hand sides that we had before. And by analogy, with the, well, level 0 formula, this is pretty much equivalent to saying that P hat is a symmetry of the action. And, well, we didn't run with into issues connected to cyclicity, simply because we were acting only with, well, we were working only with equations of motion. But if you're not convinced by that statement yet, then in the, well, remaining half of the talk, I'll provide you with some more convincing arguments than analogy with similar formula. But before that, let me just mention some checks. So basically, whatever works for n equal 4 in terms of, well, Yangian symmetry usually seems to also work for a BJM. So this was a natural point to check. And indeed, you take the magic formula that I just showed you, and it works in exactly the same way for a BJM. So that was a nice check that this formula is not just fine-tuned to work for n equal 4. And then we got a bit worried, well, maybe this is just an artifact of a superconformal symmetry of the level 1, of the level 0. And the good news is there was not. So we took the pure n equal 1 super Yang-Mills, well, which is classically at least superconformal symmetry, PSU, well, theory, PSU 2-to-1 allows you to construct Yangian, but, well, the theory is not meant to be Yangian invariant, and indeed our formula says that it's not. So indeed, the validity of the, well, magic formula is intimately tied to the Yangian symmetry of the theory. Huh? I haven't checked it. Feel free. Oh, I didn't know that either. I mean, n equal 1 I took was really just like n equal 4 with removed fermions and, well, we removed scalars. Well, one could check it. Good. So, to give you a wrap-up, like in the middle of the talk, well, what we have so far is that the Yangian of PSU 224 is a strong symmetry of the equations of motion of n equal 4. Well, we can now check for the Yangian symmetry of a given theory, as long as you have Lagrangian, so feel free to do that. And we checked it for ABJM. And now, well, we're not going to a loop level yet, but let me comment on, well, gauge fixing. Because, well, n equal 4 is a gauge theory, and if you want to do any proper computations, you will certainly need to fix a gauge at some point. So, since we have a representation of PSU 224 that actually mixes our symmetries with the gauge transformations, it's actually non-trivial whether, or not certain, whether the Yangian symmetry will still survive when I fix a gauge by introducing my gauge fixing Lagrangian and ghost fields. And, well, the good news is that in the end of the day it does, so let me just briefly go through that. So you introduce your usual gauge fixing Lagrangian, and then the action is no longer required to be invariant. It's required to be invariant only up to a BRST exact term that I have here. So S is just a BRST transformation generator, and Kj is explicitly given by this formula. So that's thing you can do on the back of an envelope. And now the question is, does it survive? Oh, sorry, yeah. So from that, well, we cannot work with the action yet. So we just vary this formula here with respect to a field, and then we obtain two terms that appear in the equations of motion once you fix a gauge. So there is one term that you would certainly expect. This one is BRST exact, but you also get a non-BRST exact contribution to your equations of motion. But that's okay. And now the question is, does it generalize to level 1? And it does as easily as you could imagine. You just put hat atop of your J, and the magic formula gets two additional terms. So that was a very easy check, at least for n equal 4, but, well, it had to be done. So it's good to know that the Yangian may very well survive gauge fixing. But all right, so I promised you a more convincing argument as to why my magic formula is equivalent to the invariance of the action. So, well, what could we use it for? And if we recall our QFT1 course, or maybe QFT2 course, and what we certainly learned there is that, well, if you have an action that is invariant under symmetry, and so is the path integral measure, that your correlation functions will satisfy the word identities. The good news, however, is that it's easy to check that for your usual Lie algebra, the strong invariance of the equations of motion is actually also enough to guarantee that result. So you can use the formula that I showed you a couple of slides ago to basically prove the word identities in n equal 4. So now, can I go to level 1? So in a sense, can I show that my correlation functions, well, in this case of, well, fundamental fields of the theory, so not, unfortunately not of the gauge invariant local operators, but can I still show that they're Yangian invariant? And the good news is that, yes, why not? So it's a relatively easy computation for a 3-point function, but you can observe also here, here, the overlapping terms, simply because you see that a square here had 2 green legs, and now one of those green legs got changed into a red leg. So this is this overlap that I already mentioned, and that appears when I act on correlation functions. For 4-point functions, of course, you get many more diagrams. You have 4-point vertex, you have, well, combinations of 3-point vertices. Good news is that using planarity, you can discard some of the graphs. That makes life easier. And in the end of the day, using, well, level 0, level 1 at 3 points, etc., you discover that also 4-point functions are Yangian invariant. And that's pretty cool because, well, for example, the invariance of the 3-level correlation functions is actually a bit stronger statement, but if you needed a proof that the magic formula is indeed equivalent to the invariance of the action, well, here it is. It was enough to establish the Yangian invariance of the correlation functions of the theory. So that was the more convincing proof, and now in the remainder of my talk, let me discuss the algebraic relations satisfied by the Yangian generators. So, given... Oh, no, so that's only 3-level. Yeah, but still, I mean, for invariance of the action, that's certainly enough. Good, so to algebraic relations, there are 2 things that one would like to check. Well, the commutation relations of the generators and the SYM relations, or, well, terrific relations if you wish. And since we mix, well, our PSU224 or Yangian thereof with gauge transformations, the computations get very involved, but still I can say a few words about the commutation relations. So if you take your p hat, which we showed that is a symmetry, with any other level 0 generator, commute it, then, well, this commutator is another level 1 symmetry. Well, almost by construction. That's a very easy observation, and due to the virtue of PSU224, you can basically obtain all remaining level 1 generators by commuting p hat that you showed, well, that we checked explicitly with the level 0 generators, well, that are also symmetries. And, well, due to commutation relations, for some j's, well, for some level 0 generators that we put here into the commutator, well, this commutator should be 0, because, for example, well, p with p is 0 or q with p. And the question is now, can we observe that? So for pure algebra, that would be identically 0, but since our transformations mix, well, global and gauge transformations, actually already at level 0, what you get for a commutator of q and p is, well, a field-dependent gauge transformation. So it basically commutes your original field z with psi bar. And then if you try doing the computation for q with p hat, what you get is a total mess, a lot of terms, and it's hard to see that this is not a new constraint, especially because, as I already mentioned, well, the commutators got changed into anti-commutators, and therefore we lose its interpretation as a gauge transformation. So, well, how do I see that what I get by commuting, well, in this example, q and p hat, is not a new constraint? So we went back to n equal 1 super Yang-Mills again. As I already told you, well, p hat was not a symmetry in that case. Well, you just couldn't make it possibly work. However, when you commute q and p hat in n equal 1 super Yang-Mills, what you discover is that, well, this commutator magically is. So for all equations of motion, you get it to satisfy the magic formula. But this theory was not supposed to be Yangian invariant in the first place. So what it means is that this well, level 1 generator has to be a symmetry only due to, well, superconformal and gauge transformations. So it's not a new constraint. And therefore, well, you show that indeed you do not introduce any other constraints than the ones that would result from the Yangian. Good. So now I can move to my conclusions. So in the first part of the talk, well, we showed that Yangian of PSU 224 is a strong symmetry of the n equal 4 super Yang-Mills equations of motion, in a sense that there exists, well, what we dubbed the magic formula that predicts exactly the right-hand side that will appear when you act with level 1 generator on the equation of motion. Well, the good news is that this symmetry is absolutely compatible with the gauge fixing. So, well, that's just good. And what I showed you in the second part of the talk is that already the magic formula is enough to assure the invariance of the, well, tree-level and planar, but still, correlation functions of fundamental fields of the theory. Well, it works for a BJM2, which is good because this is, well, another higher dimensional theory with a Yangian symmetry. And what I didn't tell you about, but, well, at some point you will hear about it, is that in a fairly convoluted way, we know how to integrate the magic formula back to get a statement for the action. Now, for the outlook, well, there are two things to be done. Well, the first thing is, well, the second one in this talk, and it would be certainly great to just go to a loop level. Well, the problem is that, well, at a loop level, everything will just start getting quantum corrections, and this will just render the computation fairly involved, but we certainly hope to get there. And the other question is, can we verify the algebraic relations that the Yangian generators should satisfy? So I already addressed the issue of commutators and what we could call the level 1 gauge transformation, but no progress has been made so far as to regarding the SYM relations, and that should certainly also be addressed. And with that, I can conclude, and thanks for your attention. Questions everywhere.
So just to like, I don't know, appreciate the significance of this invariance, is there some statement like if the action has this invariance, then at least one loop dilatation operator is integrable? Can you do something like that? Or
I would
link with the integrability the way we know it?
I'd certainly hope to, but well, we haven't proved anything of, well, of that sort yet. I mean, you would hope that, well, as long as Yangian algebra, as long as Yangian symmetry survives at one loop, then yes, but otherwise I don't know.
But just, I mean, definitely you can always define Yangian symmetry in some trivial way which any logic will be invariant with respect to, but the question is whether it has some non-trivial consequences.
I don't know.
So this statement we should prove that the equation of motion so it implies certain action of Yangian on the level amplitudes. So it should basically follow how Yangian acts in amplitudes, because you can solve classical equations by taking the free equations, you get the snake itself with this coefficients and classical solution expanded in pre-field, so in asymptotic magnitude. So this statement should be implying this other discussion of how Yangian acts on the amplitudes.
It should imply, but I mean, well, you already know how dual super and conformal symmetry works, and you can even go to twistor space to make it act, well, linearly. So in that sense, well, you probably could make it work, but I don't really know why you would, in a sense that you already have a nicer linearized action. So it would be nice to get the connection, sure, but no, oh yeah. Yeah.
Any more questions?
You said invariance of strong equation motion guarantees a modal unity. Is it specifically to this Yangian theory, or can it be generalized to any equation?
Well, I mean, it certainly already works for any of the Lie algebra type symmetries you have, because, well, it's even easier to show there. It works for Yangian as we computed, but I mean, I don't know whether it would work for, well, universal envelopic algebra in general. Probably yes, but I can't offer any proofs.
Okay. Anything more? Maybe you can just comment on the non-planar case game. You consider it hopeless, or
Was already argued in, well, I mean, was already argued in the beginning. Well, well, in principle, for level 1, you could probably be happy with just sufficiently large group. But, well, just the fact that you have level 1 doesn't really buy you much. You really want an infinite symmetry. And for that, you also want infinite n. So, you know, the Yangian will be a symmetry on in a strict planar limit.
okay.
Is there any sign for some kind of dual Yangian?
But dual conformer was already identified as a Yangian.
But can you somehow look at it from the other way around? Somehow, make some difference from.
Or you'd like
Something analogous to what we do in analysis and Wilson groups are somehow dual, but in different spaces. Could we do something like this and the level of selection?
Do you know if we thought about it? I mean, it certainly would be nice to have a, well, pretty formulation of what we have so far, because, I mean, with those nonlinear representations, with the number of fields growing all the time, it's certainly not the most beautiful formulation of the Yangian invariance of the action you could think of. So it certainly would be nice to find a more appropriate space where, well, dreaming symmetry would be realized linearly. But, well, we haven't.
Maybe it wasn't clear enough. So somehow, I guess it was discovered, dual conformal symmetry was somehow discovered in the context of scattering versus solutions, and this kind of algebraic investigation could it somehow deepen our understanding maybe of this duality of the smooths and scattering methods?
I honestly don't know. I mean,
but you could ask it already at the level of the work groups, and there, the lifeline of every part is essential. You have this key idea of that you don't have that. So
Okay. If there are no more questions, let's thank you.